Evolutionary computation is a branch of machine learning which deals with solving search-related problems. So for instance, consider regression, where the goal is to fit a curve around a bunch of data points. So in this case, let's say the line of best fit has this expression. Therefore, the goal of this problem of regression can be formulated as a search problem, where the goal is to find the optimum weight parameters W0 and W1 such that it minimizes an error function, which is essentially the difference between the predicted value and the actual target value of the points, of the data points. So this is the predicted, and this is actual. In this case, the error function is convex, and therefore you will find that the more suitable algorithms like gradient descent, which will efficiently get to your results. On the other hand, if your search space is non-convex, then evolutionary algorithms come in handy. Genetic algorithm is by far one of the most widely studied evolutionary computational techniques, which was invented by John Holland in 1970s. The algorithm is based on Darwinian notion of survival of the fittest in searching for solutions to a given problem. When you consider search algorithms, there is a fundamental balance between exploration and exploitation. Say we have a landscape and we would like to find the highest peak in this landscape. Now you could start looking for it anywhere, and as you utilize your local information to seek for the peak, what you're doing is you are essentially exploiting the current knowledge to reach the peak. Now this may or may not be the absolute result you're looking for. So this is where exploration comes in, where you acknowledge the fact that whatever results you are getting might not be the best, and therefore you would like to explore the landscape a bit better and find yourself in places which are outside the local area of knowledge that you are currently exploiting. So you may or you may not get the best results, or you might end up just through exploration hitting points which allow you to eventually reach to the best result. So that is the balance between exploration and exploitation that the search algorithms have to manage. Let's look at the details of genetic algorithm. I'll be making use of a simple problem to illustrate some of these concepts. You may be familiar with the 0-1 knapsack problem. This is where a thief breaks into a store and finds a set of items. Each item has a weight and a value. Now the problem is the thief has brought in a knapsack with a limited capacity. In this case, it can only hold at most 12 kgs of items. So the thief must decide which items to take such that it maximizes the value without breaking the knapsack. Given a problem, the first step is to represent a solution to the problem through a process called chromosome encoding. So the original definition of GA defines that an instance of a solution to be encoded using binary strings and these binary strings are called genes, and the collection of genes make up a chromosome. So this is kind of similar to genetic makeup of species. In the 0-1 knapsack problem, the solution is essentially a list of items that the thief decides to put in the knapsack, and we can represent a solution within GA in any number of ways. I'll start off with the most ridiculous of encoding techniques, so please just humor me. We have 4 items, and therefore each item can be represented by 2 bits, right? So here is our chromosome, and we can take at most, well, 4 items. So therefore the total length of this chromosome is going to be 8 bits long, and each codon, so you have 2 genes here, so each codon essentially represents the presence of a particular item. So if he decides to, let's say, take the first item, it will be 0, 0. And next, if he decides to take the third item, so this is 0, 0, 0, 1, 1, 0, 1, 1. So the third item has a coding 0, 1. And he decides, okay, that's it, only 2 items in the bag. What we can do is we'll still need to fill the remaining spaces, and what we do is we can just, once we've hit the end, what we can do is we just simply repeat the last pattern, so that this indicates to us that, well, there are only 2 items, and this is just a special pattern to mean that the list has ended. So this is one way in which we can represent the solution. Another more better way of representing the solution is to consider each gene within this chromosome as an indication of whether an item is going to be present or absent from the knapsack. So here we have, this is indicates which item 1, 2, 3, 4, and if I want a particular item to be in the knapsack, it's going to be represented by 1, so the item is present, and if an item is not present, then we put a 0 there. So in this way, the above encoding can be represented using only 4 bits. The reason why I introduced this rather ridiculous encoding scheme was to illustrate the idea that there are many ways you can encode solutions to a problem, and not all of them are going to be efficient. So in this case, if you look at it, there are 8 bits. The search space for GA is going to be 2 to the power of 8, whereas in this case, our search space is only 2 to the power of 4 bits. Right? So in this way, we would be able to get to the better solution much quicker than if you had a rather large search space. So in summary, chromosome encoding is all about representing a particular type of solution, what exactly a solution looks like. So here is a template, and what we would like GA to do is fill this template with the best possible solution in it. After we have figured out a way to encode the chromosome, GA creates an initial population of chromosomes, which are also called individuals. So these individual solutions or chromosomes are randomly created, and they represent a particular solution to the problem being solved. So here we have, if we are choosing this encoding scheme, each of the chromosome has, well, 4 genes, and the values in this, the value of these genes in this chromosome is going to be randomly selected. So this is randomly initialized. Let's say there are 4 chromosomes. The next problem-specific step is to determine the fitness function, which is used to evaluate how good a particular solution is. For this population of chromosomes, we can take each chromosome and evaluate how good of a solution this chromosome represents. So let's take the first one, which is encoded as such 0, 1, 1, 0. This simply means that the knapsack has the second and third item in it. So for that case, what is the value of the knapsack? It's going to be $5 plus $10, $15. And let's not forget to take a look at the weight. So the value is this, and the weight of this knapsack is going to be 3 plus 7, which is 10 kg, and this is less than the knapsack capacity, so we are all good. In this case, the value of this knapsack is $15. On the other hand, consider this chromosome here, which has all the items, which is saying that we take all the items and put it in the knapsack. In this case, if you look at the capacity of the knapsack, it's going to be 17 kg, which is more than 12 kg. So this will break our knapsack, and we can decide, well, this is not a good solution at all, and we might want to give a fitness of 0. So here this guy has a fitness of 15, this chromosome has a fitness of 0. So to formalize this, we can come up with a fitness function f, which will be a piecewise function, and this is simply going to be, so here this is our array of, this is our chromosome C, and it is a binary array which indicates whether the item is present or not. So what we do is simply multiply the ith chromosome with its corresponding value and sum it up. So for all the genes in the chromosome, where n is the chromosome length, we can do Ci times Vi, which will give us the value. And this will only hold if the weight of all the items selected in the bag, in the knapsack, does not break the knapsack. So this should be less than the knapsack, less than or equal to the knapsack capacity, K. So in this case we get $15 if it's all the weights are within the limits, and we should assign a fitness of 0, otherwise when the knapsack is broken. Applying this fitness function on all the chromosomes, we can now tell which particular solution is better than the others. So there are some solutions which are stronger, others are weaker, and we will see how this fitness evaluation shapes the next generation of chromosomes that we will produce by looking at selection. Now that we have determined the individual fitnesses of the chromosome, we shall use this information to select the fitter individuals to make up the next generation of chromosomes. This process is called selection within GA. There are a few techniques of selecting individuals to make up the next population. One is called the uniform selection, whereby each individual has the same probability of getting selected. This is generally not favored because what we want to do is give greater preference to stronger individuals to get selected for the next population. So a better technique is called the roulette wheel selection method. Now in roulette wheel selection, we spin the roulette wheel, and wherever it stops, that is the individual that gets selected. However, we rig it such that the individual which has the highest fitness gets a larger share of this wheel. So for instance, here the total fitness for all this chromosome is 15 plus 12 plus 24 plus 0, which is 51. And this third chromosome here has the largest fitness, almost close to half of this wheel. So this occupies 24 out of 51. That is the share given to, let's say, chromosome C3. Let me label it C3, C2, C1. Then we can have C1 here, C2 is somewhere here. Unfortunately, C4 has 0 chance of winning. So in this way, the roulette wheel is set up and we spin it. As you can see, chromosome C3 has the highest probability of getting selected for the next population, for the next generation. So let's spin the wheel and discover which chromosomes get selected. So let's say in the first spin, we might see C3 getting selected, then C1, and then probably again C3, and just to make it interesting, let's say C2 somehow manages to get in. So this could be the makeup of the individuals which are selected for the next generation. So far at the initial generation, GA came up with a random bunch of chromosomes. Then we used selection to pick the fitter ones to make up the next generation, let's say generation 1. So after these individuals have been selected, we look at the crossover operation. The crossover operation takes the selected chromosomes for mating and mixes their genetic material to produce offsprings. It is not necessary that every individual which has been selected undergoes crossover. There is a parameter in GA called the crossover rate, which governs whether a selected pair of chromosomes mate. So crossover rate is just a probabilistic value which ranges from 0 to 1. Normally we set it to a higher value, let's say 0.7 or 0.8, to allow greater proportion of the next generation to be made of offsprings. The way we can implement crossover rate is to simply generate a random number which is between 0 to 1, and if this random number is less than equal to CR, then crossover happens. Let's consider this pair of chromosome. We roll a die and discover that they will get crossed over. So the way crossover works is that it exchanges the genetic material of the individual chromosome. So in this case C3 is 1101, So there are a number of ways in which we can do crossover. In uniform crossover, we go gene by gene in the chromosome and determine randomly if which of the two parent will contribute that particular gene. So this is our offspring. We need to fill 4 gene positions. So one by one we look at the gene. So here randomly we decide, well, second parent contributes this gene here, so we put 0 here. Here we say, well, the first parent will contribute. For this gene we say, well, second parent contributes. Here the first parent contributes. So you can see the makeup of the offspring. We have other techniques called the 1-point or 2-point crossover, whereby what we do is we randomly select a position on the chromosome about which the genes would be exchanged. So let's say we randomly pick this position here. So this is 1-point crossover. It will produce 2 offsprings. Each of the offsprings will have part of the genes from both the parents. So let's say offspring 1 here takes these genes from the first parent and this gene from the second parent. So this is our first offspring, and the second offspring will take the first 3 genes from the second parent and the last gene from the first parent. So in this way, this is the makeup of the second offspring. The first offspring's makeup is this. This is why it's called the crossover. So at this stage, what we have done is we have randomly decided which offsprings are going to undergo crossover, sorry, which chromosomes will undergo crossover. So let's say C3 and C1 when had undergone crossover, and we now in their place we will see OS1, the first offspring, and the second offspring OS2, right? So they will be replaced by their offsprings. Then we consider this chromosome pair, roll the die. Unfortunately for them, they don't get to crossover, so they remain as is. So at this stage, our next generation looks like it will have 2 offsprings and 2 of the chromosomes unscathed from the previous generation. As mentioned, the crossover rate determines which pair of selected individuals end up getting recombined to form offsprings. Now, suppose if we set the crossover rate on the extremes, let's say if we chose the crossover rate as 0, what happens then? As you can see, the makeup of the next generation will consist of the chromosomes, direct copies of chromosomes from the previous generation. Since there is no recombination, you will not have any offsprings being produced. So with each passing generation, what you will see is a selection of chromosomes which are copies from the previous generation. There is no new information that's going to be produced, and therefore you will be stagnant with whatever chromosomes were the fittest in the initial randomly generated population. On the other hand, if you were to set your crossover rate to 1, that implies that every pair of selected chromosome undergoes crossover, and so your following generation will always be composed of offsprings. This might present a problem because it's not necessary that the offsprings that are produced will be any fitter than the original parents. And so in this way, if you have a very high crossover rate, let's say if all the pairs are getting crossed over, you will lose information, you will lose some knowledge that was represented by the feta chromosomes in the previous generation. So that's why generally we set a crossover rate which is slightly high, but not too high that it completely transforms the next generation with only offsprings. Another way to deal with this problem is when we are doing selection, we introduce the notion of elitism, whereby what we do is we can take the top n fit individuals and copy them straight into the next generation and do not touch them, do not use them for crossover. So in this way, we are assured that we will be preserving the best solution in the current generation to stay alive in the coming generations. In summary, the crossover operation represents the exploitation part of the search algorithm because we exploit the fitness measure as we combine the genetic material of the fitter chromosomes to produce the next generation of offsprings. After the selected individuals have undergone crossover, the next operation is mutation. So the mutation operation in genetic algorithm introduces diversity within the population so that the search algorithm does not necessarily get stuck at local optima. In essence, mutation represents the exploration part of the algorithm, which allows us to discover unexplored areas with the intent of finding better and better solutions and not getting stuck at subpar solutions. So this could be the local, this is the local optima, and what we are looking for is the global optimum. And there is a tendency with GA that things can get stuck at the local optima, and without mutation, we will not be able to explore the diverse areas and possibly miss out on the global optima. Just like crossover has crossover rate, mutation has a mutation rate parameter within GA which governs which of the randomly selected genes will be mutated. So it's a probabilistic measure from 0 to 1, and given a gene, given a chromosome and a gene location, the mutation rate tells us which of the genes will undergo mutation. So what happens in mutation is that suppose we have a chromosome as such, we randomly select a gene, and if it is meant for mutation, what happens is in mutation there is a bit flip. If it's a 1, it becomes a 0 becomes a 1. So in this case, the new chromosome after mutation looks like this. So fundamentally, for each of the chromosomes that you see, there might be few genes which are getting flipped. So this introduces genetic diversity, and normally we don't want it too much. So imagine a case where mutation rate was set to 1. What will happen then? Well, every gene in every chromosome will get mutated, which means your population will be inverted, right? It's not something that you want, because your search then ends up becoming completely random search. On the other hand, if your mutation rate is set to 0, then none of the chromosomes in the following generation will have any mutation in it, and this reduces this totally eliminates the genetic diversity in that population, which means you are bound to get stuck to local optima and not be able to discover global optima well. So generally we want to have a mutation, but not too much. And typically we set the mutation rate to be around 0.1 or so. Putting it all together, given a problem, we first came up with a representation of the solution in the form of chromosome encoding, and GA used this template for chromosome encoding to create an initial population of individual chromosomes which were randomly populated. And with this initial random population, we applied a fitness measure to determine how good these randomly created chromosomes were. Based on the notion of survival of the fittest, we selected individuals or chromosomes for the next generation based on their current fitness measure. So the fitter individuals had a greater chance of getting selected. From these selected individuals, based on the crossover rates, some individuals underwent crossover operation, whereby the genetic material was exchanged to produce offsprings. And some of these resulting offsprings um, underwent mutation, which is a way of adding genetic diversity in this population. And once we are at this stage, we have a new generation of chromosomes, and therefore this process continues. So for this new generation, we reevaluate the fitness measure and carry it out. So this is, in a nutshell, this is the genetic algorithm. Of course, we can modify it slightly a bit. After the fitness measure, we don't want to be doing this forever. So what we want to do is we want to check if the solution has been reached, whatever we are looking for. It could be the number of generations we allow GA to run, or the specific value specific value of fitness we are looking to find. So if the solution has been reached, then we stop our GA. Otherwise, it goes on to the next generation, with the hopes that with each passing generation, the chromosomes will evolve to represent better and better solutions.